Hello everyone, good morning. So I'm Dr. Abdul Pasha, Assistant Professor, Institute of Aeronautical Engineering from the Department of Electrical and Electronics Engineering, Hyderabad. So we are in the course of Power System Operation and Control. So here we discussed so many key issues related to power system operation and control. So this is about control area concept and numerical analysis for a given turbine mode. So in these concepts, we are going to learn some simple examples based on the turbine cases and how control area is going to be designed, what are the criteria we are going to assume to make over and to sure about the control area concepts. So here this describes a numerical analysis that is based on two generating stations. 1 and 2 have full load capacities, that is about 200 megawatts and 100 megawatts. So at the frequency of 50 Hz they are going to be operating. So two stations are interconnected. So this is station 1, this is station 2. So two stations are interconnected here. So they are supposed to be operating with a frequency of 50 Hz. So that means they are making a full load capacity about 25 megawatts. So speed regulation of the two stations, station 1, station 2, and induction motor and synchronous generators are given, and they are to be set at 4%, 3.5%, and 2.5%. These are the ranges which are provided usually. So here, coming to the analysis part, we should assume that a power of a megawatts flows from station 1 to station 2. Then total load on the first station will be treated as 75 plus whatever the assumed load case, that is A megawatts. That is going to be added in megawatts range. Now total load on the station 2 becomes 50 minus A. Why? Because here 75 is given and 25 are given with a full load capacity. Then total load on the first station will be added with 75 plus A. And total load on the second station becomes 50 minus A in megawatts range. So here we will treat a percentile drop in speed at a station 1. That may be taken as whatever the total load of the first station and the second stations, they are said to be a value of 4%. That divided by the 200 value means here it is about full load capacity of the first one, that is 200 multiplied with whatever the assumed case of 750, that will be added to the assumed case, that is A. So this will be provided like that. Similarly, we may write percentile drop in speed at station 2 as a 3.5 by 100, which is about 50 minus A. So reduction in frequency will supposed to results. This is due to the power flow from first station through the interconnected of motor generator set. So we are using the induction motor here, and the percentile drop in speed at motor jet set becomes 2.5 by 25. So this will give a suitable value with a reduction in frequency at station 1 plus reduction in frequency at motor generator set. So this may results to the reduction in frequency at station 2. So therefore, if you are adding to each other this value and this value, that is about 4 by 200 into 75 plus A plus 2.5 A by 25. So that is equivalent to 3.5 by 100 into 50 minus A. So simplifying to this case, you are getting 0.02 into 75 plus A plus 0.1 A, which is equivalent to 0.035 to 50 minus A. So when you are writing for this expression, so 0.02 multiplied with 75, that gives about 1.5 value, and if you are multiplying this with A means 0.02A plus this 0.1A. So which may multiplying with 0.035 into 50, that gives 1.75, and if you are multiplying the same coefficient with the A, 0.035 into A gives minus 0.03A. So here when you are writing in terms of A coefficients, 0.02A, 0.1A and 0.03A, that may result into adding to this value here. That means 75 minus 1.5, 1.75 minus 1.5, which is give to 0.25 value. So here we have already 0.15A, that is 0.25. So A becomes 1.66 megawatts. So that is a power of A, 1.66 megawatts flows from station 1 to station 2. This may happens usually. So total load at station 1, that is first station, is 75 plus A. So A already we obtained calculated value. How much? A equals to 1.666 megawatts. This value is going to be added here. That will be adding means 76.666 megawatts. Now total load at station 2 becomes 50 minus A. So 50 minus A means 1.666. So 48.33 megawatts we are going to obtain. So if the system is designed with the 200 megawatts, 100 megawatts with the two generating stations, so they are going to be separated by a separate reactants and feeding that about 25 megawatts of each case, then they are going to make the resultant of this one. Another example is a 125 MVA turbo generator or alternator operates on full load, and they are supposed to be treating at a frequency of 50 Hz. So a total load of 50 megawatts is suddenly reduced on the given machine. So steam valves to the turbine is commences to close after 0.5 seconds. So this is due to the time lag in the governor system. So assume that the inertia to be constant and H value becomes 6 in kilowatts per kVA of the generator capacity. Now we need to calculate the change in frequency that occurs in this time. So that we need to calculate change in frequency. So here by definition of the H, we know that amount of energy stored by capacity of the machine is going to be treated. That energy stored at no load is 6 into 125 into 1000. This gives a value of 750 megajoules. So that means excessive energy input to rotating parts is about 0.5 S. That means here we have about 1000 value. So 0.5 into 1000 gives 25 megajoules. So as a result of this, what happens means there is an increase in the speed of the motor. Hence an increase in frequency is going to be takes place. Then total kinetic energy is expressed in W suffix K. So this becomes W suffix Ke naught into F naught plus delta F by F naught whole square. So now new value of the F becomes, substituting for this, so 750 as this one and 25 by 750. So F naught plus delta F by F naught. F naught is here 750, delta F is about 25, and again F naught is 750, 750 plus 25, 775 by 750. That is multiplied with frequency value about 50 Hz. This gives to 50.83 Hz. This is the new value of the frequency that we are going to reach. Coming to the control area concept, what happens? So in general, in real practice case, the system of a single generator that is connected or fed by large and complex areas, which has rarely happens or occurred. Then several generators connected in parallel, located also at different locations. So they will meet the load demand of such geographically large areas. So all those generators may have the same response characteristics to the changes in load demand case. So it is possible to divide a very large power system into sub-areas in which all the generators are tightly coupled so that swing in with change in load or due to a speed change or setting is going to be takes place. So that means such area where all the generators are running coherently or collectively is known as control area points. So in this area what happens means frequency will be same in steady state and dynamic conditions it will be achieved. So for developing such suitable control strategy, we are going to introduce a control area that can be reduced to a single generator. So that may also treated with the speed governor mechanism and connected by load on the system. Next case is incremental power balance of control area. What happens with the incremental cost? So this influences load effectiveness of the system. So in this case, we should develop a dynamic model. That means in terms of its incremental power and the frequency dynamics. So that control area is connected through the lines. So that we supposed to observe here. So now we should assume that control area experiences a real load change. That real load change becomes delta P in megawatts. So due to that actions of the turbine controllers, its output increases by delta P in megawatts. So net surplus power in the area becomes delta PGI minus delta PDI, which will be absorbed by the system in three aspects. So that is by increasing the area kinetic energy WKE at the rate of dWKE by dt, and by an increased load consumption that should be expecting at all typical loads because of the dominancy of the motor loads. So they experience some increase in the load case, which is about B equals to dou PD by dou F in megawatt per H with the speed of the frequency case. So by increasing the flow of the power through the tie lines with the total amount, then which will be defined to the positive for outflow of the area case. This may be treated usually. So here we are going to represent interconnected control area system. This is connected by control area J, control area I, control area V. So all these will follow with control area K. So delta PGA minus delta PDI gives dWK by dt plus B delta F plus delta tie line power. So tie line power is the difference between the scheduled real power and actual real power through the interconnected lines, and it is supposed to be taken as the input to the load frequency control system. Now if you identify the single area, what happens means whatever the first two terms on the right hand side of the expression what we seen here, that should be expressing a generator load model with the subscript called I, that is to be absent. If the third term is absent, it means that there is no interchange of the power between I area and any other area. So thus it becomes to be single area case. So a single area is a coherent area in which all the generators swinging into the changes in load or speed change or setting, and in which the frequency is going to be assumed to be constant throughout both in static and dynamic conditions. So this single control area cannot be represented usually, but it should be represented by isolated power system network that containing turbine, speed governor, generator and load model cases. So here it will describes about block diagram representation of the single area. So block diagram of the isolated power system network, which will be treated as the essence of the single area system. That means it is same as the block diagram whatever we earlier seen here, like this. And what happens to this condition means, so this is usually treated with the block diagram of LFC of isolated power system network of third order model case, that is also represented. So there are two incremental inputs to the system. So they are change in the speed changer position as delta P as reference power input, and second one is the change in the load demand, that is represented with delta P. So what happens in this section means we will analyze the response of the single area system to the steady state analysis in three aspects. One is constant speed changeover position with variable load demand in uncontrolled case, constant load demand with variable speed changer position with controlled case, And third one is variable speed changer position as the load demand is existing in the system. So here speed changer position is constant. That means in uncontrolled case with the given model delta PC equals to 0, the response of an uncontrolled single area load frequency control can be obtained as considering a simple case, whereas the speed changer has a fixed setting, which means that delta PC becomes 0 and load demand alone will change. So such operation is known as free governor operation or uncontrolled case, since the speed changer is not manipulated here, and it may also treat that control to achieve better frequency constancy range. So for sudden step change of the load demand delta PD by S may exist. So for such operation, steady state change of the frequency is to be estimated from the block diagram itself. So this is the representation of the block diagram. For an isolated power system setting to delta PC equals to 0, then the reference section will follows with KSG by 1 plus TSG blocks, and the control blocks associated with KAT by 1 plus STT, and the referral section will be represented with the delta PD of S as KPS by 1 plus STPS as function of delta F of S. So as delta F of S is existing with the KPS by 1 plus STPS by 1 plus KSG by R into 1 plus STG by 1 plus S tau. This is with into delta PD of S by S. So when this will be simplifying case with a negative sign, KPS by 1 plus S tau PS into KSG KT KPS by R by 1 plus S tau G into 1 plus S tau T into delta PD of S by S. So applying to the final value theorem, we show that delta F under steady state as delta PC equals to 0, if it extends to 0, delta F of S that becomes applied at delta PC of 0. Finally, we are reaching to the constant KPS by 1 plus KPS KT KSC by R with multiplied with one of the load demand constant delta PD here. So gain K is fixed here for the turbine, and K is fixed for the power system network also. So gain K of the speed governor is easily adjusted by changing the lengths of the various links of the linkage mechanism. So K is so adjusted such that K is approximately equals to 1. So therefore equation can be simplified as delta F as minus of KPS by 1 plus KPS by R into delta PD. So also we know from the dynamics of the generator load model, KPS equals to 1 by B, where B coefficient is dou PD by dou F. So dou PD by dou F is 1 by F PI constant in per unit system as megawatt unit per change in frequency is expected. So that delta F is minus 1 by B 1 plus 1 by PR as delta PD case. So therefore delta F is minus of 1 by 1 plus 1 by R into delta PD, as it is equals to minus 1 by beta into delta PD case. So this factor beta is B plus 1 by R, which is known as the area frequency response. This is most important in the characteristic manner, as AFRC is considered, our area frequency regulation characteristic is going to be treated here. So that expression gives here the steady state response of the frequency to the changes in the load demand case. So speed regulation usually so adjusted that changes in frequency are very small, which is about to order 5% from no load to full load. So that representation is the linear relationship between the frequency and load for a free governor operation. So with that speed changes, it will be set to a given schedule frequency about 100% under full load condition. So the droop or drop on the slope of the relationship is represented with a minus 1 by B plus 1 by R. That power system parameter is generally much less than 1 by R case, so that B can be neglected. That means which results to delta F as minus R into delta PD. So the droop of the frequency curve is mainly determined by the speed governor regulation R, then that percentile frequency with percentage of the load is going to be considered as one of the droop, that is 1 by 1 minus B plus 1 by R, that is as minus R case. This is taken as steady state load frequency characteristics represented for speed governing mechanism. So this may be represented as one of the slope curve, which is representing one of the drooping parameter. So The increase in load demand delta PD is meeting under steady state conditions is partly by the increased generation, that is delta PG. So this is due to the opening of the steam valve conditions. So, and it will be partly decreases the load demand due to the droop in frequency. So increase in generation is expressed as delta PG, that is minus 1 by R delta F. So substituting for delta F for the above equation, then delta PG becomes minus 1 by R into minus 1 by 1 B plus 1 by R delta PD, which is equals to 1 by R into R by BR plus 1 as delta PD, which is 1 by BR plus 1 delta PD case. So, and a decrease in the system load, which will be expressed as B delta F, then B into minus of 1 by B plus 1 by R delta PD gives B into R by BR plus 1 into delta PD. So, that is BR by BR plus 1 into delta PD. So, from the above expressions, it is observed that the contributions of the decrease in the system load is much less than the increase in the generation case. This may usually happen. So, these are some of the references which I have considered to deal with this, and we can extend more analysis with various controllers introduction into the system that gives smoother and better response to the net. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.